Chapter 5 is gases. I just want to mention right at the beginning of the video, your exam, I curved it 5 points. It's all I can really do because I had two 97s and a 95, but I did add 5 points to your Blackboard grade. That also being said, those of you who have me for lab, your lab assignment is posted on Blackboard under the assignment section. I also posted a video on how to do the calculations that I'm requiring. Please read the lab and read the instructions that are on the assignment, and then check out the video, which is on our YouTube page here, of how to do the calculations. If you're still having issues, then email me and I'll try to help you out the best I can. All right, so chapter 5 is gases. The whole thing we're going to deal with is being in the gaseous phase. So gases are so important that there's essentially a whole entire chapter based just on gases. Okay. So we're going to start with something called the kinetic molecular theory of gases. All right, the word kinetic means motion, movement. Movement of gas molecules is what we're talking about here. Okay, so kinetic energy is the energy an object has due to its motion. It actually has a formula of mass times its velocity squared. Okay, so it's actually 1/2 times the mass times the velocity squared. But kinetic means motion. Okay, so the motion of gas molecules. This theory makes assumptions about the size of the molecules, the motion of the molecules, and the energy of the gas particles. Okay. So the slides basically shorten kinetic molecular theory to KMT, so that's what that means there. All matter consists of tiny particles that are in constant random motion. We call that random motion, sometimes you see it in biology as Brownian motion. Okay, they move in a straight line until they collide with other particles or walls of the container that are holding it. So we don't move in zigzags or curves or anything like that. So the first thing is that they are in constant motion, our gas particles. They move in a straight line. Their motion is in random direction, so it's not that all of them are moving to the right, or all of them are moving to the left, or all of them are moving up and down inside the container. They're all moving in random motions, but they are moving in straight lines until they collide with something. And then the angle of collision and things like that, with those of you who have to take physics, you'll see that. Or, take a physical chemistry class, you talk about things like that. But they do move in a straight line until there's collisions. Okay? The second part of the kinetic molecular theory says that gas particles are much smaller than the distances between them. Okay? If I have a gas in a container, the majority of the container is empty space. Okay? So that's why when we were back in like chapter 1 and talking about gases, we said that they're very highly compressible. The reason they're highly compressible is due to all of this empty space in between the gases. Okay? So most of our volume, like it says, is empty space. They're far apart. Okay? There's no attractive or repulsive forces between gas molecules. Gas molecules really don't interact with one another until they get close and collide. Okay? So they're independent. All right, nothing's holding them back like a surface of a liquid or the shape of a solid. There's nothing really holding them back from moving around. And again, the motion of one particle is independent of the motion of the other particles because they aren't interacting with one another. Part 3. If a gas molecule combines or collides with a wall or another gas molecule, okay, they do not lose their energy of motion. Okay, it's called an elastic collision. No kinetic energy is lost. So if you think about a car, and if a car ran into a building, okay, or a tree or something like that, the car most likely is going to stop. Okay? It's going to lose its kinetic energy. It's going to lose that motion of energy. If it was, say, a car going down a hill, okay, and it crashed through a building, it's going to lose that kinetic energy it picked up by coming down the hill when it collides with the building. I need a drink here. Back-to-back lectures killing me. Okay. Gases don't do that. When they bounce off something or hit something, they retain their total amount of kinetic energy, so that stays constant. And since it's not disappearing, okay, and essentially getting lower, we call it an elastic collision because it's bouncing back and keeping the same amount. Part 4. All gases have the same average kinetic energy at a given temperature. So temperature matters how much energy a gas has. Gas molecules are going to speed up when the temperature rises. They're going to slow down when the temperature gets lower. But it doesn't matter if I'm N2 or O2 or Cl2 or CO2 or carbon monoxide. If I'm a gas, I have roughly the same amount of kinetic energy at a given temperature no matter what it is. Okay. So the amount of energy a gas substance has is directly related to the temperature. And again, the temperature has to be in Kelvin. That's important. Okay. All right. And we can figure out the kinetic energy of our gas molecules by taking the mass times their velocity squared times a half, like I mentioned earlier. But one key I want to highlight is that word Kelvin. And that's going to come back. Okay. Now, 0. Absolute 0, which is minus 273.15 degrees centigrade. Okay. At absolute 0, that's the lowest temperature possible. The theory states that at this, chaos ensues and all the physics we know, okay, basically goes to the wayside. All motion of our molecules, so if there's no motion of our gas molecules, we were watching them and we wanted to know our temperature, we would assume we were at 0 Kelvin, that we were at absolute 0. Okay? Higher temperature, higher motions. No motion, I'm at absolute 0. Okay? So absolute 0, all chaos would ensue. All right, what about the terms diffusion and effusion? Okay. Diffusion describes the movement of one material through another. Okay, particles diffuse from a high area of concentration to low. High to low, high to low, high to low. All right, you probably talked, for those of you who had a biology class, you talked about diffusion, okay, with passive transport. You might have done it in labs, putting a drop of water into a beaker of cold water, a beaker of hot water, and watching it spread out. Okay, that's moving from an area of high concentration to an area of low concentration. The word effusion means gas escaping through a tiny opening. Okay. Different than the word diffusion. Now, since we're talking about passing through a material or escaping through a tiny opening, the heavier the molecule is, the slower it is to effuse or defuse. So, the greater the mass of the particle, the slower the effusion or diffusion, depending on what you're looking at. You might have done this in, I don't know if you did or not, in your biology lab, where you took an auger plate with holes in it and you put a couple different colored dyes in it. You might have used like malachite green and crystal violet or something, and then looked at the diffusion rings around the plate at the end of class. I know when I used to do bio a long time ago, bio labs, we used to do that lab to show diffusion and show that the size of the molecules, Trenton said he did it, the size of the molecules, they diffuse slower. Some of them can't get through the auger as fast. Some of them, the circles were huge. Okay, same thing here. That's what we were looking at, really. Okay, and here they're showing diffusion versus effusion, moving from an area, all right, before, after. We're going to get to spread out, where effusion is, hey, let's get these particles out of this tiny opening. Okay. So what about pressure? All right, gases exert pressure. Pressure is a measurement of force over a unit area. Okay. Gas pressure, if we're being more specific, is the force exerted by a gas per unit surface area on an object. Gas pressure comes from all of the collisions that are occurring by the gas molecules with each other and with the object itself. Okay, and specifically with the object that the gas is being held in. The gases might bounce off each other, but then when they go and bounce off the walls, that's what's exerting the pressure. And as you know, this says billions and billions of these. I mean, if you think about it, a mole of gas, so 1 mole of gas, which is, let's just say it's chlorine gas, Cl2, is roughly 71 grams per mole. Well, 71 grams of chlorine gas really isn't that much, and that has Avogadro's number of gas molecules running into one another. And imagine, and then running into the sides of the containers. So pressure is going to be exerted by those gas molecules. Atmospheric pressure, also known as air pressure, results from the collisions of air molecules with objects. Now, the way to think about it is a column of air coming down on Earth. The closer you are to the surface of the Earth, the more you're going to feel the atmospheric pressure. As you move up in altitudes, the atmospheric pressure becomes less and less. Okay? Because the density of said atmosphere becomes less at higher elevations. So, sea level versus the top of the Colorado Rockies, Denver. Not saying that's the top of the Colorado Rockies, but Denver, Mile High City, versus, Death Valley. You're going to feel a pressure difference between those two because the density of the atmosphere is different in Denver than it is in Death Valley. Okay. And we'll talk about how that affects a lot of things. The term vacuum means empty space with no particles and no pressure. That is a truly empty substance if there's no particles and no pressure in there. Then we've created a vacuum. All right, so here's a list of the periodic table of some of our elements that exist at 25 degrees Celsius, which is roughly room temperature, and 1 atmosphere, okay, of pressure. And that's a unit of pressure. ATMs, or atmospheres, is a unit of pressure. So H2, N2, O2, F2, Cl2. And then your noble gases all appear as gases from the periodic table. Okay. Here's some other molecules. 25 degrees Celsius, 1 atmosphere. So over here we have our elements, and then here's our molecular compounds. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. So if you look at these up here, if I place this in water and these in water, these three here are strong acids. This is a weak acid. But they're gases. They're gases that end up getting bubbled through water to make our acids, in case you're wondering how they make the acids. You have carbon monoxide, carbon dioxide, ammonia, okay, is a gas at room temperature. And I know what you're going to say, but I go to the store and I buy ammonia. That's an ammonia solution. That's not pure ammonia, okay, and it's a liquid. All right, it's actually an aqueous solution, which we know that now. It's not really a liquid. You're buying an aqueous solution. It's not a pure substance. It's ammonia and water. But then people look at you when you tell them that and say, potato, potato. And then you say, no, no, no. There's a difference between a liquid and aqueous solution. And then they don't want to talk to you anymore. If they do want to talk to you still, then, like I said previously, keep them as your friend or family member. Okay, so what's our physical characteristics of our gases? All right, whoops. Gases assume the volume and the shape of their container. A gas will fill the entire container. We talked about this. You put cyanide gas into an area, it's going to fill that entire area and kill whatever's in there. It's not going to just sit in the corner. It's going to continue to expand and expand until it can't expand any further due to the limitations of said container. Gases are the most compressible state. Go back to our kinetic molecular theory. Why are they the most compressible state? They have large gaps in between the molecules that are just empty space that we can compress those molecules to fill that empty space. Gases will mix evenly in a container. Now, here's a key if you're taking notes on this to put next to this. If I mix two gases in a container and they don't react, okay, so they don't create a new compound, they're just two gases individually in a container, they will act like they are the only gas in the container. And what I mean by that is they will fill the entire container and pretend like the other gas isn't there. We as humans and as, solid objects, we can't do that. Okay, if there's two people sitting somewhere, we can't just assume we're the only person in the room and stretch out across the room. We'd be hitting the other person. Gases, since they have that large empty space, a gas enters the container and says, this is all mine. And then another gas enters and says, this is all mine, and expands like the other gas isn't even there. Since they have a lot of dead space and their mass to volume ratio is going to be small, okay, a small number, they have very, very, very low densities. Okay. So gases' volumes will change great with pressure. Gases' volumes will also change greatly with temperature. We're going to talk about that in a little bit here. Gases have relatively low viscosity. Okay? Remember, viscosity, or I'll tell you what viscosity's definition is. Viscosity means that its ability to flow or inability to flow. The more viscous I am, the less my molecules can move over one another. Okay, so gases, molecules can move freely, so they have a low viscosity. Low densities under normal conditions. Miscible, that's a fancy word, meaning they'll act like they're the only ones in the container, and they will mix no matter the ratio. Okay, so miscible means mixing no matter the ratio, and it's due to the fact that they could stretch out the way they do. They'll take the volume and the shape of their container, and they're the most compressible. So again, here's our gas molecules. The gas is going to fill the entire container. All right. Here we have liquid. Liquid still takes the shape of the container, but it's bound by the surface because the interactions are a little bit more. And as a solid, I'm going to sit there doing my own thing. I'm not going to take the shape of the container. I'm just going to have my own distinct shape and my own distinct volume. So we already talked about pressure and we talked about the atmosphere. Gravity is what's pulling the atmosphere down. The closer I am to the surface, the more gravity is going to pull that down to the surface. And that atmospheric pressure is going to be exerted on the objects. The further up we go, the less gravity has an effect on that atmosphere. The atmosphere is less dense, and therefore, okay, we have less pressure. So you can picture, essentially, the atmosphere coming down like a column of air. We're at sea level, we're at 1 atmosphere. And as we move further and further up, okay, our atmosphere, or the pressure felt by said atmosphere, is less. This is why when we fly, we have to have pressurized cabins. We adapted to our area, wherever we're living. People in Denver are going to be adapted to that higher altitude. You go out there and you have medical conditions, and my brother, for one, he was out in Colorado. He went to see Red Rock, check out Red Rocks in a concert out at Red Rocks last summer. And he was saying when they were walking through one of the mountain passes, he actually had to go over to the medical tent because he felt faint. Now, my brother has pre-existing conditions too, but the thing is that he's not adapted to that larger altitude. And the thing about that larger altitude, it's interesting with pressure, because pressure directly affects boiling point. Okay, so boiling water in Denver, baking in Denver is going to be a little bit different than baking in, Nanacoke. Oh yeah, exactly, Trenton. They have to do, so people climbing mountains have to essentially take years of training, okay, and to do stuff like that, so that their bodies have to adapt to those different environments. Yep. Same thing with deep sea divers. They have to adjust their bodies because below sea level, now you have the ocean's pressure, not talking gases here, but the actual mass of the water and the pressure of the ocean crushing. So that's why if you ever went overboard on something, if you ever watch Deadliest Catch, I don't even know if that show's still on, and the crab pots go to the bottom of the ocean. If you got stuck in one of those, forget about drowning. Yes, you'd drown, but the ocean's going to crush you on top of it. Which leads me to Lion King is a great movie. And essentially Aladdin is horrible science. Because when Aladdin's at the bottom of the Arabian Sea and Genie pulls him up, Genie essentially kills him and gives him the bends. That's why deep sea divers have to level off, because they have to adjust to the pressure difference. What's even more interesting, since you brought up mountain climbers, I was going to bring this up a little bit later. Since boiling point is affected by atmospheric pressure, when you get to a certain point on a mountain, depending on how high the mountain is, I'm not talking the mountains around here. I'm talking, real mountains like K1 and all of those. When you get to a certain point on like Everest and things like that, water will start boiling at such a low temperature that it won't steep tea. Because why water boils at a high temperature, at the surface of the earth, is because of the atmospheric pressure. So the water vapor has to counteract or equal the atmospheric pressure pushing down. And the more heat that's required to get that vapor pressure up, okay, then the hotter the water is going to get. Well, if I have no atmosphere or very low atmospheric pressure in a high altitude, my boiling point, the amount of energy required to make something boil, is going to be very, very low, or a lot lower than 100 degrees Celsius. And therefore, you might not even be able to make tea because the water's boiling. If you continue to remove pressure from the surface of water, you could have water boil at room temperature. Boiling doesn't mean hot. Boiling means water being able to escape to gas phase. And at the beginning of Gen Chem 2, we start talking about colligative properties and phase diagrams and all of this other stuff. And you could actually see the physical line where I could just alter the pressure and get stuff to boil. See, the thing is, atmospheric pressure is constantly pushing down on us. We're adjusted and adapted over time to that atmospheric pressure pushing down on us. The reason why, say you go to Colorado and you'll have a difficulty breathing, and here's another reason why a lot of the Olympic training things and people who train or are athletes train in higher altitudes. Your body at surface level is taking in oxygen in perfect unison and giving out CO2. The amount of oxygen we take in is then picked up by red blood cells. And the reason when we breathe we take in oxygen is this equilibrium, symbiotic, I don't want to say symbiotic, that's not the right word, but like an equilibrium reaction. We have the perfect pressure inside with the perfect pressure outside to take in oxygen and exhale. So that's why if we get a lung puncture or something like that, we have difficulty breathing, because that internal pressure that's helping us breathe, okay, is making it essentially more difficult to breathe because we've interrupted that equilibrium, that diffusion-effusion thing. Yeah, homeostasis, Yeah, Rob, that's not even really the real word there. But yeah, it's more like that. But as soon as I have a lung puncture or something like that, and that internal pressure in our lungs changes, then inhaling and bringing in the correct amount of oxygen becomes more difficult. Well, now we're adapted to sea level. We go to a higher elevation. We're having a difficulty breathing at a higher elevation. The reason being is that our internal, how we've developed, how we've adapted to the environment isn't used to having that less atmospheric pressure outside. So it's harder to get oxygen in. So what does your body do to adapt to that? Because people are living in Denver. So it's not like, people are choking to death when they live in Denver. So what's happening? Well, one of your body's responses is it'll start to produce more red blood cells. And the reason it'll produce more red blood cells is because, well, you're not taking in as much oxygen. So if I produce more red blood cells than what I normally have at sea level, the red blood cells will pick up all of the oxygen. I will be more efficient in my oxygen usage than I was. So what an interesting fact is, a lot of athletes, especially some of them that were supposedly caught cheating, were training at larger facilities, or higher altitude facilities. They were building up their red blood cell count. They were freezing those red blood cells, that plasma and platelets and all that fun stuff. And then before a race, were injecting themselves with their own blood, therefore increasing their red blood count. Well, if I increase my red blood count, I'm going to use oxygen more efficiently. If I'm going to use oxygen more efficiently, I'm going to get fatigue less. Or I'm going to have less fatigue. Or I'm going to fatigue at a slower rate. Therefore, I'll be able to last longer. One of the key components, there was a coach that coached basketball in Denver in the early 80s, and his key component was, we're going to run up and down the court. We're going to take a shot in the first 10 seconds of the shot clock. We're going to keep running up and down the court. And his idea was more possessions, more scoring. But it actually worked out pretty well in Denver for the fact that teams that would travel into Denver would get tired a lot quicker for the fact that they weren't adapted to that higher altitude environment. And the same idea with baseball. Okay, playing at Coors Field, why is there more home runs? Why are, pitcher ERAs up higher? Well, less dense air, ball's going to just travel further. Okay? So there's a lot of stuff in your everyday life. Well, here's one thing we really don't consider. And you probably have done this reaction, not with an alcohol metal can and sucking the air out of it. You probably did it more with a high-C juice box. Okay? So with your high-C juice box, you would blow air into it after it was done or while there was juice in there and shoot it at people. All right? If you're anything like, me and the goofballs that I went to grade school with, all right, that's stupid stuff we do at lunch. All right? But once you sucked all the juice out and the box would look like this can over here. Well, the thing is, as long as there's air, so if I had an empty beaker, it's really not empty. Okay? There's air in that beaker. If I were truly empty and there was no stuff in that beaker or in that aluminum can or in that juice box, it would be crushed by the atmosphere. Because the atmosphere is pushing down on us. The thing is, we don't feel it because we're pushing back. Our internal skeletal structure, our liquids in our bodies, we've adapted where we're pushing back. Our containers are full of air, so they're not really empty. So if you want to be the world's biggest optimist, if someone tells you, is the container half filled or half empty, you could be the ultimate optimist and say it's completely filled. Not only is it half filled with a liquid, but the other half is filled with air. Because if it was completely empty, the atmospheric pressure would crush it. And that goes back to my Aladdin analogy with water. Aladdin would be dead at the bottom of the Arabian Sea. Okay, the water would have crushed him. Genie couldn't save him, and even if Genie got there in time before the water really crushed him, by pulling him out of water that fast, and if you haven't watched Aladdin, get out from under your rock and watch Aladdin, all right, especially with Disney Plus and not being able to go do anything anyway. I've been catching up, okay? There's nothing wrong with it. I watched The Incredibles, never watched it. I know it's an older movie. I know some of you weren't even born when it came out, but I watched The Incredibles, okay? I just rewatched Zootopia. I just rewatched, I watched Cars 1, 2, and 3 for the first time, so yeah. Yeah, I'm being very active in my, my life right now. All right. But anyway, in Aladdin, they pull him up from the bottom of the water. That's called getting the bends, and it'll destroy blood vessels, organs, things like that. Okay, so Genie should have really leveled Aladdin off before pulling him out of the Arabian Sea. So you are getting crushed, in theory, by pressure. The thing is, you are pushing force back on the atmospheric pressure. So nothing is truly empty unless I create a vacuum and remove all of the air particles and have the can look like this. So how do we measure pressure? Okay, here comes the fun stuff, measuring pressure. All right, so here we go. Pressure is measured in a unit called atmospheres, shortened by ATMs. Pressure is also measured, okay, in a unit called millimeters of mercury. Now that's really weird because millimeters is a measurement of length. So what does a measurement of length have to do with a measurement of pressure? Okay. And what happens here is we have to draw ourselves a barometer. Now, again, not an artist, and there's a picture in the slides. I don't know what the heck I just drew there. But essentially a barometer is a long tube with markings on it that's put in a tray of mercury. Okay. And what happens is atmospheric pressure pushes down on the mercury tray and has the mercury move up the tube. The distance the mercury moves is the pressure. And that's why it's measured in millimeters of mercury. They actually call it the change in height, or delta H, of the mercury. But it's essentially how much did the mercury move inside the barometer. And there's a better picture, okay, in the slides I'll show you than what the heck I drew. All right, right there. Now, in America, being American, when you watch your weather forecast and they give you the barometric reading, in the good old USA, they tell you inches of mercury. It's doing the same exact thing, but instead of using the metric system like everybody else, they're going to report it in inches. I know I should let it go and just accept it, but I don't. Okay. Meteorology is a science. Science uses the metric system. Let's report everything in the English system and Fahrenheit. Okay. Now, there's another way to measure gases that we make in lab. The barometer is great. The barometer is great, okay, for measuring atmospheric pressure. All right. But what if I want to make a gas in lab and measure its pressure? Okay, so then we use something called a manometer. Okay, and the manometer is pictured right here. There's two types. There's a closed-end manometer, and there is an open-end manometer. Okay, so here's how it works. Here's our mercury level in the J tube. Okay. We have a flask with nothing in it. We create a gas in lab and we hook up the test tube or whatever to it. The gas pushes up and causes the J tube mercury to move. By doing so, there's a difference in the height from here to here. And whatever that pressure is, or that change, is the pressure of our gas. The open end takes a little bit more math. The open end is open to the atmosphere. So I got two things going on right now. I have the atmospheric pressure pushing down this way, and the pressure of my gas that I created pushing this way. Okay, in all three examples. In our case here, the mercury hasn't moved, which means that this gas is pushing with the same force as this gas here. Okay. That being said, I can assume that if I know my atmospheric pressure, I know the pressure of my gas. Over here, atmospheric pressure is pushing, my gas is pushing. The mercury is moving in this direction, which means the atmospheric pressure must be pushing with a greater force than my gas. So the pressure of my gas is equal to, what's my atmospheric pressure minus this difference. On this last one, the gas is winning. Atmospheric pressure is losing, so atmospheric pressure is greater than or less than the gas pressure. Therefore, my gas must be the atmospheric pressure plus this additional amount that it's winning. So my gas is equal to atmospheric. My gas is less, so it's the atmospheric minus this amount. Here, it's winning. Okay, the gas is the same. Okay, winning. So the gas is the atmosphere plus this distance. Okay. Now, how about some units? Wow, it's really raining here now, guys. The lights just flickered, so if I lose you or internet connection, I'll continue to video as long as I don't lose power and then upload the whole thing. But I'm almost done for today anyway, because we are going on almost 45 minutes here of nonstop lecture. All right, here's what we got. Units that we can use, and you should be able to convert. I will give you the conversions on an exam if I need you to convert, but you should be able to do conversions by now. So you should be able to convert in between all of these here. So, pascals and kilopascals you'll see in physics. Okay, physics and physical chemistry. You'll see pascals and kilopascals. It's the System International unit for pressure. Okay, these are all equivalent to each other. So 1 atmosphere is equivalent to 1.01325 times 10 to the 5th pascals, 101.325 kilopascals. Atmospheres, okay? Chemistry, that's what we use. We also use millimeters of mercury. Chemistry, medicine, and biology, okay, uses that. You'll see torr, 760 torr. Chemists can also use that. Okay. PSIs, or pounds per square inch, is an engineering term. Your tires in your car, so if you go to fill them up, you know, at Sheetz or wherever, and they have the digital one and it beeps at 32, they're telling you your tires are 32 pounds per square inch. Filling your tires cold versus filling your tires warm makes a difference. You should drive the least amount possible before filling your tires up. Because filling your tires up warm, the gas is going to expand. Go back to the kinetic molecular theory. So when it beeps 32, you might not have really 32 in there. 32 pounds per square inch on a hot tire is different than 32 pounds per square inch on a cool tire. When your tire cools, then the gas is going to not be expanded anymore. Maybe you have 31 or 30. Just a little tidbit there. Bars, 1.01325 bars. Meteorology uses bar. They won't use bar when they're talking to us on the news, all right? But they might. But usually you never see bar. But in a meteorology class, you'll use the term bar for pressure. Okay? So for homework, you could try sample problem 5.1. All they really want you to do is convert 291.4 millimeters of mercury to torrs, atmospheres, and kilopascals. Okay, so they just want you to do a conversion problem there. I'm not going to get into the gas laws until next class. I think I gave you enough gas. That sounded perfect, didn't it? I just gave you enough gas. I gave you enough information to start gases off. Okay, again, I don't want to overload you. Okay, so we're going to start gas laws on Tuesday. So, homework. Let's go back here. Okay. Homework in chapter 5. Sample problem 5.1 from the slides. Okay, then we are on. Let me see what page we're on here. 248 in the book. I can't see that far away. I'm getting old. Five point one. All right, 5.1 to 5.3. Five point eight to 5.14. Okay. So there's the homework. Okay. Also, again, I added a 5-point curve to the exam on Blackboard. So your grade's been corrected, 5 extra points. I couldn't do any more than that. I had 2 97s and a 95, so there's not much more I could do, but you got 5 extra points. If you have lab with me, your assignment's been uploaded. You also owe me the metathesis assignment, but your assignment for this week has been uploaded. I also did a video on Blackboard and help you through the calculations. Please read the instructions. I gave you numbers in the instructions to use. And I also posted the lab in the assignment. There were a couple, Trenton. Okay. All right, so let me turn this off.